All right, stat students, we are moving on into chapter 9. So chapter 9 is more of hypothesis testing. And instead of just one group of data, we're going to be looking at two different groups. So today we're looking at testing the difference between two means using the z-test. So we're testing the difference between apples and oranges. Okay, so suppose a researcher wishes to determine whether there is a difference in the average age of nursing students who enroll in a nursing program at a community college and those who enroll at a nursing program at a university. So here they're not interested in what the actual age is. They just want to know if there is a difference. So the hypotheses would be H naught and H1. So H naught is mu1 equals mu2. So the means of the two groups are equal is the assumption, and then we're trying to see if they're actually different. Okay, and so that would be your hypotheses, and you would define like mu1 to be for the community college and mu2 to be the university. Another way it can be written is that the difference between mu1 and mu2 is 0, which means they're equal. Like if I move mu2 to the other side, it's equal. And then the opposite of that would be not equal to 0, so that the means are different, that there is a difference. But we are going to use that method. Okay, so when we are sampling, there's two types of sampling. So we have independent samples and dependent samples. So independent samples, the subjects selected for the first sample do not influence the subjects selected for the second. So you have two groups, 25 people in each. And they aren't influencing the others. You have different people. Dependent samples is when you have a selection of the subjects in the first group influence the selection in the other group in some way. So it could be like the same person, a before and after type of test, or like determining if their right foot is larger than their left foot. But it's dependent in some way. So we will talk more about dependent samples in the future. Today we are doing a z-test, which is going to be for independent samples. So both samples are random. They have to be independent. And the population's standard deviation must be known. That's how we do a z-test. Remember, a t-test is when we don't know the population standard deviation. You have to use a t-test. Okay. So we're going to be selecting pairs of samples and comparing the means of the pairs. So the population means don't need to be known. We're just comparing to see if those two samples are different. So the population means are assumed to be the same. It doesn't matter what they are. They could be 5 and 5, or they could be 10 and 10, but they're the same. Okay, so our formula for the z-test for comparing two means is this. So x1 bar and x2 bar, those are your sample means. So these are sample. And then these are your hypothesized mean, population means. So remember that if mu1 is equal to mu2, that's hypothesized, then mu1 minus mu2 is going to equal 0. Sometimes they will assume, and I think I say this in the next slide, but that the difference is 3. So that part is not always 0, but for our purposes, it will be. And then divided by your standard error, which is going to be standard deviation squared over n1 plus standard deviation squared. So if the difference is not significant, that means that the means are from the same population. So the two different groups come from the same population. If the difference is significant, then that means that those two samples are coming from different populations. The means are different. not the same. So community college versus university, the same, you're getting those samples from the same population versus different people go to different colleges. Okay. The test can also be one-tailed, so it could be right-tailed, so mu1 is greater than mu2, or left-tailed, mu1 is less than mu2. You are going to use the same steps for traditional, for the traditional method that you did in the last chapter. Okay, so let's go on to our example. So first thing, we're going to read through this. So a study using 2 random samples of 35 people each found the average amount of time for those in the age group 26 to 35 years spent per week on leisure activities was 39.6 hours. And those in the age group of 46 to 55 spent 35.4 hours. Assume the population standard deviation for those in the first age group found by previous studies is 6.3 hours. And the population standard deviation for the second group found in previous studies is 5.8 hours. So that's the part that tells us that we're doing a z-test, because we know the population standard deviation. At alpha equals 0.05, can it be concluded that there is a significant difference in the average time each group spends on leisure activities? Okay, so first thing is our hypotheses. So we're going to assume the population means are the same, but we want to know, can it be concluded that that there is a significant difference? And it just says a significant difference. It doesn't say greater or less than, higher or lower. So we're just going to say not equal to, and that is our claim, because that's what we're trying to conclude. Okay, then step 2 is our critical value. This is a z value. Our alpha is 0.05. So we need to find this is two-tailed. So we need our z sub alpha over 2 for our critical values. So you look for 0.025 in the z table, or you look in the t distribution. And for two tails, or 95%, that's the third column in your t distribution. All the way at the bottom, you see 1.96. So our critical value is plus or minus 1.96. Okay. Now I'm going to, I'll draw my little picture here. So we have 1.96, the negative and the positive. So our rejection region is the tail. Okay, so for calculating my test statistic, I'm going to go to a new page. So for step 3, our test statistic is x1 bar minus x2 bar minus mu1 minus mu2 all over the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so let's write down our values. So x1 bar, sigma 1, and n1. So if we go back, the first age group, we're going to say this is our first age group. So the n is 35 for both. 39.6 is our average, and then the standard deviation is 6.3. So 39.6, 6.3, and 35. Then we need x2, sigma 2, n2. We know n is 35, and then we go back 35.4 and 5.8. 35.4 and 5.8. Now we plug those in to find our test statistic. So 39.6 minus 35.4. And the mu1 minus mu2, remember, is just 0. And then we have 6.3 squared over 35 plus 5.8 squared over 35. When you solve that, you are going to get 2.90 as our z. So let's go back over here. So step 3, our test statistic is z equals 2.90. 2.90 is falling in the rejection region. So we are going to reject H naught because 2.90 is greater than 1.96. It's in the rejection region, the shaded parts in the tail. So then we wanted to know if we could conclude that the difference was significant. So we can say there is enough evidence to support the claim that the means are not equal. Okay, so that's our first example using the traditional method. The second one is using the p-value method. Remember that when you're doing a p-value method for a two-tailed test, you have to double your p-value. So if my test statistic my test value or test statistic is 2.90, we look that up in the Z table. And you're going to get a big number, but remember we have to take 1 minus that number, whatever it was, to get our p-value because it's only in the tail. So, or you could look up negative 2.90, and your p-value you get is 0.0019, but that's in each tail. So you have to multiply that by 2 to get both tails added together. So your actual p-value is 0.0038. So remember to double your p-value if you're doing a two-tailed test. Okay, so here is our next example. A researcher hypothesizes that the average number of sports that colleges offer for males is greater than the average number of sports the colleges offer for females. A random sample of the number of sports offered by colleges for males and females is shown. Assume, or at alpha equals 0.10, is there enough evidence to support the claim? Assume sigma 1 and sigma 2 are equal to 3.3. So we're going to say that X1 bar is, the first group is males, and you can just plug all those in, find the average. I'm going to give that to you. It's 8.6, and then they gave us sigma 1 is 3.3, and N1 is 50. And then the females are going to be X2, and that would be 7.9. When you add those up and divide by 50, sigma 2 is 3.3, and N2 is 50. Okay, so our first step is to find our hypotheses. So again, remember that I'm assuming the mu1 is equal to mu2, and we want to see, is there enough evidence to support the claim? So that means the claim is going to be in the alternative hypothesis. It says that they're saying the average number of sports for males is greater than for females. So mu1 is males greater than females, and that's our claim. Okay, so then for step 2 is our test statistic, because we are doing this by the p-value method. Okay, so our test statistic, z, is where I subtract x1 minus x2, so 8.6 minus 7.9, minus mu1 minus mu2, so that's minus 0. And then we have our standard deviation squared, so 3.3 squared over 50 plus 3.3 squared over 50. So our test statistic is 1.06. Okay. Then for our third step, this is the p-value. That's where we go to the table. So I'm going to look up, remember that this is a greater than, so it's a right tail. Okay, and we found our test statistic is 1.06. I'm looking for the area under the curve to the right. So when I look up the value in the table, I get 0.8554. But remember, I have to take 1 minus that because I want just the tail, and the table gives me to the left. So you could look up negative 1.06 to get the answer right away. So this gives me 0.1446. Okay, so my p-value is 0.1446. That's the value I got. Okay, so remember, if the p-value is less than alpha, then it's you're going to reject the H naught. Okay, so my alpha level was 0.10. So my p-value is greater than alpha of 0.10. So I do not reject. The reason we're not rejecting is that it's probable that it came from this center region. If it comes from that, it's probable that happened just by chance and that it's not actually statistically significant difference. So we do not reject H naught because it's greater than alpha. And then step 5, our claim was the alternative hypothesis. There is not enough evidence to support the claim. Okay. Just so you know, we talked about this earlier. You can say that your hypothesis is that they're 3.2 years older, and then your alternative hypothesis is that it's a greater than 3.2. We aren't going to see that on your homework, though. Okay, and then confidence intervals. So in this chapter, we're going to do the hypothesis test and then the confidence interval. The confidence interval is another way to figure out if you're doing a hypothesis test, if you would have rejected H naught or not. That was funny. So if the confidence interval contains 0, then the hypothesis is not rejected. So it's probable that since it's in the confidence interval, 0, then it's probable that the difference is not significant because mu1 minus mu2 is 0. It'll make a little bit more sense once we do an example. If the confidence interval does not contain 0, then the null hypothesis would be rejected. Okay, so this is going to look very similar to your Z test statistic. And I'm going to write it when we do our work. I'm going to write like plus or minus in just this part like I have been doing. Okay, so we are going to use the data from example 1. So if we remember, our Z sub alpha over 2 was 1.96. we're finding the 95% confidence interval. So our confidence interval, I'll write the formula here. Plus or minus z sub alpha over 2, sigma 1 squared over n1, plus sigma 2 squared over n2. Okay. So we plug in our data from that first example. Plus or minus 1.96. And then I have 6.3 squared over 35 plus 5.8 squared over 35. So I get 4.2 plus or minus 2.8. So then my confidence interval is 1.4, which is less than mu1 minus mu2, less than 7.0. So this interval does not contain 0. Okay, so that means that we would reject H naught. Because this is our 95% confidence interval. We're 95% confident that the mu1 minus mu2, the true mean lies, the true difference lies in there. So if we're 95% confident that it's in there, 0 is not. So we're 95% confident that it's not the H naught. And that we have evidence to support. So if we went back up to our first example, we did reject H naught. So we're finding the same thing there. Okay, so that is it for 9.1. Let me know if you have any questions.